everyone. It's a pleasure to introduce today's speaker, Professor Demetrios Papageorgiou. He's a professor in applied mathematics at Imperial College London. Formerly, he was and I guess he crossed the Atlantic to be closer to home. He's a fellow of the American Physical Society and of the Institute of the Mathematics and its Applications. He's a co-editor-in-chief of the IMA Journal of Applied Mathematics. We collaborate with Demetrios within the framework of the Code3 project, which is funded by RIF, which supported his visit today. So today he's going to talk to us about the evolution of PDEs arising in multiplayer physics.
Thank you very much. Great pleasure to be here. It's my first talk at the Cyprus Institute, and of course I know lots of people here. It's been a great visit. So I'll start kind of general, then get into, I should speak into that, yeah? Yeah, okay. Because I usually move around too much, so I'll try and stick. Okay, this works. So I'll start kind of general. So our main interest is wave dynamics, wave phenomena that occur across scales. So what do I mean by that? It could be kind of kilometers, hundreds of kilometers. Those are tsunami events generated by earthquakes, or down to the wave scale, a meter to 5 meters, down to millimetric scales. These are falling liquid films on an incline, and then way down to micron, nano type scales. And again, these are waves between two fluid interfaces. So my main interest is to kind of find unifying type equations and unifying type mathematical ways of addressing such equations. So today I will talk more about this area of this diagram. But just to get an idea, here are some simple partial differential equations that describe some of these phenomena. So if we start with wave motion, this is the celebrated Kurtberg-de Vries KdV equation that gives us, this was the first time that solitary waves were found. So this is, when you hear solitary waves, immediately you think of this PDE. So it's a balance, it's about some steadiness, of course, but the balance between nonlinearity and dispersion. So this is just two physical things going on, nonlinearity and dispersion. Then if we go further down the system size, further down the scale, we get equations very similar to this. And if you look at this, there are more derivatives. This is the Kuramodis-Washinsky equation. And why is this interesting? Well, this is interesting, again, nonlinearity, mixing things up. But in addition, there is a fourth derivative here with a plus, which is diffusion. So it's a bit like a second derivative on the right-hand side, but higher diffusion. So we call this hyperdiffusion sometimes. But then there's negative diffusion as well, okay? Because this term has the wrong sign. Usually for the heat equation, we see it on the other side with a plus sign. So this is negative diffusion. So what does this system do? Again, this is just like this is solitary waves. This is the easiest system, nonlinear PDE, that gives you chaotic dynamics, spatial temporal chaos. And you can extract all these features you see from simple logistic map type things. And then if you go further down the scales, you get these thin film type equations. This is very similar to this, but much more nonlinear. Okay, so what we call this a degenerate parabolic equation. The reason being that there's a u cubed there, and when u goes to 0, it means you're losing all your high derivatives. Okay, because the d dx. So if this is 1, this is kind of the same as that, right? more or less, not one exactly. But these two terms will be the same as that. But this will degenerate, will go to zero. If it goes to zero, you lose your diffusion. Yes. Of course, you can interact. Yeah. Yeah, that's a great question. Thank you for asking that, because it is all based on deriving these equations from first principles from the equations of fluid dynamics. So you're right. This term is dispersion. There is no viscosity whatsoever here. In this case, this term is surface tension. And that's why there's a high curvature, high derivative. And this term is inertial destabilization. It's to do with destabilization due to sufficiently large inertia. And here it's there's no inertia here. That's why we get the degenerate PDE. But yes, these are all derived from first principles. And hopefully, and I'm probably already running very late, but hopefully I will show you how these are derived in a slightly more complicated example than these. Okay, so the objective is to do engineering on the small scale, particularly microfluidics, where things are fairly stable unless you have external forces doing things. For example, you can push these systems out of equilibrium by electric fields, magnetic fields, oscillations, all these different things. Okay, so the basic feature in these small scales is that surface to volume ratios are large. And therefore surface tension is important. And in particular, things like surface tension, electrical charges, all these surfactants, all these different things will play a role. And I want to consider something, another physical effect, and that's imposing shear flow on these things. So in other words, they will be flowing due to either gravity or pressure gradients and so forth. So that's the objective. And here's some examples. So this example we already saw. So this is a falling liquid film where you feed, so it's an inclined plane, and you feed the liquid from the top, and then as things evolve, they become unstable, first two-dimensional, then three-dimensional, and then by the time you're down there, that's spatial temporal chaos already. You can characterize all that. Now, this is called an open system because there's only one liquid and then it's air, and you ignore what happens above. Whereas these types of problems have two fluids with an interface in between. Yes. So this would be yeah, I'm not going to talk about things with surfactants in them. So this would be yeah, water, oils, something that has constant viscosity, and the viscosity doesn't depend on shear and so forth. At some point, I'll show something about viscoelastic fluids as well. But always interfaces, yeah, that's the, yeah, or more than two fluids too, like it's even more interesting. So a paradigm two fluid example is a quet flow. So this is one liquid and then another liquid on top, and then what you do is you shear it. So you move the top plate to induce a shear. So this is the simplest case. And this is an example of an experiment where because you run out of length, you do it in a circular quad device. So you have a toroidal section, and the top plate moves, and then if you're kind of away from the walls, I mean, this is exaggerated, the depth. If you're away from the walls in the middle, it looks like a two-dimensional quad flow. So that's the idea. So these are experiments I will be comparing with. And this is a picture of what the waves look like in one of this class of experiments. And this is what we get with the type of theory I'm going to try and develop. Okay, just by deriving PDEs and getting the solutions. So these could be pure shear type flows, or you could also have a driving pressure gradient, in which case these would be piecewise parabolic profiles as we get from exact solutions of the Navier-Stokes equation. So where do these waves come from? Okay, so these are kind of very classical fluid dynamical effects, hydrodynamic stability results. So what we know is that if I have a single phase, so in other words, one liquid, no interface, and I shear it, and I do a hydrodynamic stability via the Sommerfeld type equations, right? You linearize and then you get your Sommerfeld equations. Then plain quad flow, which would be in this case, so just one shear, is linearly stable at all Reynolds numbers. Okay, it doesn't mean it's not non-linearly unstable, but it's definitely linearly stable for all Reynolds numbers. And experimentally below about 1200 or so, they do not see any perturbations growing. Plain Poiseuille flow, on the other hand, again, without an interface, just a parabolic profile, is linearly unstable for Reynolds numbers bigger than 5,000 or so. So again, small Reynolds numbers should be stable. The moment you put an interface in, these things change. In fact, you can show that the moment there's an interface there, the interface will become unstable. There will be an unstable interfacial mode that will be active at any Reynolds number, irrespective of how small it is. It doesn't have to be critical and above at any Reynolds number. And the instability is long wave. Of course, it depends on the various parameters. And this is what has been determined, is if you have, so let's just think of these two-layer flows, fluid one, fluid two. I will always have fluid one below, fluid two above. And they have different viscosities, mu1 and mu2, the same thing there, right? Different viscosities. If the thinner layer, right, so this is the result, it just comes from analyzing the Sommerfeld equations. If the thinner layer is also the more viscous, then you get waves, then it's unstable. Okay, so that's the result. So if mu1 is bigger than mu2, then it's unstable. So it all depends on the geometry of the configuration and the ratio of viscosities. The mechanism is quite complicated. Don't want to go into it here, but mathematically you can show this in a straightforward way. So what do I want to do? What I want to do, and in particular, I want to consider systems like this, having the experiments in mind. Okay. And what I want to do is to follow the instabilities into the nonlinear regime. Okay, I don't want to stay linear. I want to go nonlinear. And the way we will do this is doing an asymptotic analysis of the equations of motion with just one assumption. The only assumption will be that this layer is thin compared to that layer. And that happens in experiment. That will be the only assumption I will make. Well, actually not exactly the only one, but That's the main assumption. So we'll do this, derive reduced dimension models, partial differential equations, solve them, and then solve the Navier-Stokes equations directly, compare them, and then also compare with experiments. And then at the towards the end, the last third or so, we will look at multi-layer flows with interfacial slip, right? In all these situations, I assume that the two fluids have no slip between them. But there are systems where you get interfacial slip. So we will replace those boundary conditions with Navier slip conditions. So let's go through, and I think that goes back to the question earlier of how are these derived. So the idea is that I may have more than two fluids, so a bunch of multi-layer configuration like this with lots of interfaces. And then the Navier-Stokes equations are valid in each region. There could be other physics as well, like electric fields or surfactants that diffuse and convect and also go into the interface, temperature, and so on. Okay, so this is kind of the multi-physics environment that we want. And we actually considered most of these things. So what are the equations? So the equations of motion are the Navier-Stokes equations, incompressible Navier-Stokes equations written here. Here I gave them for Newtonian flows, but these could be viscoelastic. Okay, so you can modify with your favorite viscoelastic model, and I'll show something on that. And then really this is complicated enough, but the additional complication is that the boundary of where you need to solve these equations is changing in time. So you need to determine that as well. So I need boundary conditions at the interfaces, and I'll show you what those look like next. So if I suppose that there's some shape, a function that describes the interface between fluid 1 and fluid 2, then I can write down boundary conditions on this interface. And again, this comes from balancing forces. Okay, so it's all mechanistic. And these are the boundary conditions. One boundary condition says the fluids are viscous, is that the velocities are continuous. Okay, by this angular brackets, I mean the jump in quantities as I go from one fluid to the other. Okay, so as I go from fluid 1 to fluid 2, this is the jump. So U is continuous. And then I have tangential balances, tangential stress balances, says the tangential forces are continuous. And the normal forces are discontinuous, and that jump is equal to the curvature, surface tension. So that's where surface tension comes in. Now, if you have surfactants, then there will be additional terms there. If you have electric, magnetic fields, this will get modified and so on. But in principle, it's all the same. More complicated, but all the same procedure. And then I have a kinematic boundary condition at the interface that says that the interface is a material surface. Okay, so it's a sharp interface. And kappa is the curvature, and that's what it is in 2D. Okay, so these are nonlinear, right? These are to be evaluated at y equals h, where h is not. That's a big complication. Now, so let's try and develop this a little bit asymptotically. So in other words, if I consider that previous system as very complicated, how would I try and simplify it in a rational way? Well, one way is to assume that the waves are very long compared to a typical length size of the system, which is the height of the channel. Okay, and this leads to long wave, fully nonlinear long wave equations. That was a little bit That's exactly where that last equation I had in the slide with the PDE models. The degenerate PDE comes from this type of model. Now, sometimes you're not really justified to do this. And here's a situation where you're not. In fact, if you have a quad device and you have a thin layer, either at the bottom or the top, then you can't, I mean, you can say if you want, you can say that the wavelength is very long compared to this size as well, but that's not really the case. Usually the wavelength of the waves on this layer, even though it's thin, is of the same size as the thickness of the channel. Okay, so the natural length of the system comes in. It's a little bit like if people are familiar with water waves or internal waves, a little bit like the Benjamin Ono type extension of the KdV equation. That's where you do those, and that's why you get always non-local terms, as we will see. So the idea, so I will concentrate on this case. So the idea is that there is a thin layer, and I'm going to look at waves that scale with the size of the system, okay, which is what we see in experiments. So this is probably very busy. I don't need to go. Okay, so very, very briefly, we do formal asymptotics, where in the thin layer, I take advantage of the fact that it's thin, and I can do the mathematics more easily, and then couple it with what happens in the thick layer. Okay, so there's lots of details, and then you have to match the two things together. And of course, there's all sorts of mathematical questions, like you get PDEs. How do you know they're any good? So if you can manage to prove global existence and so forth, then it should be a good model to try and push to large values of the parameters. And that's one of the things we try to do. Okay, so here's how one would do it. I'll just sketch it. We don't have enough time. This is how one would do it if I had the thin lower layer. So epsilon, let's say in an experiment, this you would non-dimensionalize, that's 1, and epsilon is something like 0.1, 10% of the thickness, or even smaller. That's what you see in experiments. But here we assume it's epsilon and try and do an analysis based on epsilon, where I will allow for the interface to deform, but have a wavelength which is as big as that. Okay, so the wavelength will scale with the channel. Lots of parameters, right? Reynolds numbers, viscosity ratio, that's an important parameter. There's a capillary number and the Weber number that we can express in terms of capillary and that. So a lot more parameters than the single phase problem. So how do you, so the objective is to find an equation for S. Once I find S, I can get everything else. Yeah. You can have gravity. Yeah. In fact, I think I do have it in the equations at some point. Yeah. Okay, so how would you do this for a thin lower layer? Well, what you do is you introduce another variable, a new variable zeta, which describes the thin layer. And then, so these are technical details, so I don't want to bore you with this, right? So, and then you look, so I'll say it differently. I mean, this is all symbols, and then you can do the algebra. But the idea is the following. Without this, the interface is flat and the layer is undisturbed. So you ask the question, how small, what's the smallest amplitude, smallest epsilon to some power I can have where this perturbation will become nonlinear for the first time? That's the idea. That's why we call it weakly nonlinear. So if you do all that, you can write down expansions, Okay, it's not important exactly what the powers are, but everything follows from the equations. And you can solve this problem, but then you need to also solve what happens in the upper region. And this is where things become interesting, because in the upper region, you get elliptic type operators, you get Laplace type operators, because you no longer have a separation of scales, right? The y is no longer smaller than the x. The x and the y are the same. Therefore, you get the full Laplace coming out. And that's what we want to do, match these two. So if you do all these things and you couple everything, you end up, okay, some details, but never mind, you end up with this equation. And this is kind of beginning to look similar to what I had in the beginning. HHX, that's my nonlinearity. This is surface tension. And this is due to the coupling between the two regions, between what happens below and what happens above. So in other words, I need to solve something in the upper region and then evaluate it at the undisturbed interface to couple it to the H. So this is a function of H. What does it look like exactly? Well, it looks like this. Okay, again, this is, don't worry about that for the moment. But what it really looks like is that you need to go to the upper region and solve a Or-Sommerfeld type equation. So this is a quasi-static Or-Sommerfeld equation. The reason it's quasi-static is because I have a very slow time scale of evolution because of the thinness of the layer. So once I solve this, right, once I solve this, and what I need to evaluate this is f double prime at 0. So I need to solve this 2-point boundary value problem, okay? And once I solve that, then I can get this n, and then it goes in there. So from a technical point of view, I don't even look at that, right? The Fourier transform of this term is simply n times the Fourier transform of H. That's all it is. Okay, I know it's spectrum, but it's non-local because of this, of the fact that I have an elliptic region I need to address. Okay, so when there's slip, this gets a little bit more complicated. But let's see what happens a bit further down. Once you rescale, so you can rescale this thing so that you put a 1 there. You just rescale space and time, and then in two L periodic domains, you can write down this non-local term is really just the Fourier series. Right? So in Fourier space, it will simply be n times h hat. And then I know point-wise, right? I know for each k, for each integer k, I know what that is by solving that previous problem. And okay, and lambda is a crucial parameter. It has the viscosity ratio coming in. So this is called viscosity stratification. If m is bigger than 1, then I get stability. If m is less than 1, I get instability, which is exactly what was found from the Or-Sommerfeld. Yeah, I mean, you're there. There is, yes, there is. Yes, yeah, you're right, there is. It's but this is this would be because this is always stabilizing, right? So the way you deduce this is that this is always stabilizing. So the only way it can be destabilizing is if the real part of this is negative, and then you can go back and back these out. But there will be a K dependence in the full spectrum, and it will always be well opposed because of that. Yeah, the short waves will be stable. So And then you can then go and solve this numerically. Yeah, going back to Panagiotis' question, this is the spectrum. So it's minus lambda times the symbol, that I know numeric. Actually, I know it analytically as well. I'll show you later. And then short wave stabilization. Now, what's interesting is to look at large K. So large K typically tells you, if you have a PDE and you look at large K, it will tell you kind of intuitively the behavior, the well-posedness of the PDE. If this S, right, the growth rate, if it doesn't decay for large K, it means you're in trouble. Right? That would be Kelvin-Helmholtz type instability. So in this case, what happens for large K, this is dispersion, right? There's an I there. So this is some kind of a non-local dispersion. This is surface tension, but then this is what the viscosity stratification does. So it introduces a constant value at infinity. Okay, so again, this agrees with the physics that comes from the full or Sommerfeld equation that has been classical. And another detail is that if the Reynolds number is 0, there is no inertia, then I lose the instability. I have purely dispersive waves. So if you like, if I switch off surface tension as well, it's kind of a generalized KdV type equation. So it's kind of water waves with a non-local dispersion. And that's a lot of interest in those problems lately. So here's some experiments. Okay, so the main thing I want to say here is that from the size of the experiments, we could back out the size of the wavelength I need to use for this PDE, and then I can solve the PDE and compare it to the experiments. The experiments, what they do is they put a probe at the interface and they measure the height of the interface at a fixed point. But that's if it's a traveling wave, then that signal will give you a periodic traveling wave, right, modulo the speed of the wave. So Andreas asked about gravity. It can be important. So it's there. Of course, it's always stabilizing. So it should damp things a bit. So, and here's a comparison. Again, this is just to show that this model does really well. And there were many attempts to get some of these results by extensions of the PDE, but it looks like you have to take into account these non-local terms. It's very crucial. So we're quite happy with these comparisons. Okay, and then we also did direct comparisons with Navier-Stokes simulations. They're also quite good. Now, one interesting thing that was found in the experiments was a bistability, they called it. So they fixed the Reynolds number, the speed of the plate, and then they observed that you could get two types of waves. You could get this wave or something that was twice that wave at the same Reynolds number, and they were both stable. So it's like it's a nonlinear system, so you can have two different states that are stable. So we wanted to see if we could get this from the model equation, and there were ad hoc attempts to do it by adding terms, and they weren't successful. So what we did is to do kind of a detailed mathematical study with Sally Tanvir, and we recast this a little bit so that we put a viscosity nu in front of the fourth order derivative. That's just a bit easier, keeping everything 2 pi periodic. And it turns out that if you look at this equation, this is the equation we had before, the solutions are area functions and their integrals. So you can actually write down solutions to this, and you have very good control of the asymptotics. So that's what we did. And again, I don't have time to go into any of these things, but we also showed a global existence of these things, and also showed that these all these solutions would compute, these traveling wave solutions would compute. They do exist, and this is done using this quasi-solution technique, kind of like it's like a nonlinear Newton, but using contraction mapping theorems. So let's look at some numerics. Okay, so we looked at traveling waves and looked at their stability as well. So what I'm showing here is for a certain value of the parameter, 1/20, that just tells you the wavelength in a sense. K equals 1 means that it's a unimodal type solution, right? So it covers the whole domain, one period. K equals 2 is a bimodal, it repeats. Okay, so that's the bistability type thing. And what's shown here is some norm, it's the energy norm versus this parameter lambda, which is the bifurcation parameter for different Reynolds numbers, okay? 20, 50, 100. Where you see dashes, it means the traveling wave is unstable. Okay, because you can check the stability by just calculating the Jacobian and finding the eigenvalues as you compute, and then there are bifurcation points, and then it becomes stable again. But what we see in all cases, if you look at branch 1 and branch 2 here, they're solid at the same value of lambda, right, at the same value of the parameter. So they're stable, so they both exist and are stable for a single value of lambda. So that means bistability. Okay, it means I can have both of these solutions for a single value of the parameter. And this is generic actually for different Reynolds numbers as well. So this explains the bistability observation that was seen in the experiments. Check time. Okay. So these are some results. The blue, I can't remember what's stable. Yeah, the blue is stable, the red is unstable. So these are what the solutions look like on branch 1. So they fill the complete period of the device. And these are bimodal, so these repeat twice around the toroidal region of the device. And they look very similar to the experiments. And we need to do a direct one-on-one comparison, but that's something to do next. Okay, some extensions, you can extend all this to viscoelastic flow. Okay, you can put this Oldroyd B fluids in both regions and do the same things. So that's why I wanted to say in the beginning that the formalisms are all the same. You just do different physical things, and you can also do surfactant effects. And we did a lot of work on that. Just out of interest, the viscoelastic partial differential equation is this, but there's one little detail here is that now I have an additional term which involves the Weissenberg number. So this is the fact that the flows are viscoelastic, and there's instabilities due to streamline curvature, essentially. Now, this zeta, of course, is always positive, and this is negative diffusion. So this will always destabilize the flow. So in a viscoelastic system, even at zero Reynolds number, where this is pure imaginary, and therefore this is dispersive, I will still get instability. And in fact, you can even drive the system to chaos. Okay, these solutions are actually chaotic if you run them long enough and do the return maps and so on. So it's an example of chaotic dynamics at zero inertia, and it's all due to the elasticity of the fluid. Okay, now for the last part, I want to talk about slip at interfaces, and I'll begin with some evidence and some simulations. I'll show this and then try and model this and see what we can get. So one there's a paper about 20 years ago by Zhao and Makosko, where they did experiments where they were extruding polymers, polymeric fluids. In many cases, lots of these layers. I think they had as many as 64 or 128. It was a power of 2 for some reason, which I don't know why, but so lots of layers. And then they would check the flow rate coming out. And then they noticed that the flow rate was, if you assumed no slip at the interfaces, so if the velocity was continuous, the flow rates were way off. But if they allowed for slip at the interface via an obvious slip condition, then they could back out from the experiments, from their observations, they could back out a slip length. So that was the first evidence. The explanation they gave was that there was reduced entanglement where the two polymers met, and as a result, there was slippage of course, on the micro scale, there isn't, but if I view it from the macro scale, then there's slippage in this very tiny layer. A more interesting to me study anyway was the molecular dynamic simulations of Koplik and Banavar. And I think they've done it with some more recently, where again, they tried to model the entanglement by playing with the interaction laws between the molecules. So they called them miscible and immiscible systems. And I think you can do that with the Leonard-Jones potentials, bearing the parameters. And then they did simulations. And this is what they find. If this is a Couette type flow, so again, a shear at the top, nothing at the bottom. So this is shearing, or maybe it was shearing at the bottom in this case. And this curves, the circles are for the miscible case. So there is entanglement, and then it looks like there is no discontinuity in velocity. Everything is continuous. But if the potentials were such that they were immiscible, then you see this very clear jump in velocity, which is reminiscent of slip. The same type of thing happens for Poisson flow. They did it for pressure-driven flow. Again, if it's miscible, sorry, you get kind of a parabolic profile like Poisson. But if it's immiscible, then you get kind of piecewise parabolic. And then they also fit their results to a Navier-Slip law, and they backed out a Navier-Slip coefficient, which was of order 1. Okay, so it looks like from a mathematical modeling perspective, it looks reasonable to assume to replace the continuity of velocities with a Navier-Slip condition. This is what we did. Now, of course, without having to taking values of the slip from the experiments, okay, and the simulations, which they're order 1, so that's quite good news. So this is what the flow would look like, for example, if you had slip. So there will be a discontinuous velocity profile. It's always linear because these are wet, right? Simple shear flows, but there's a discontinuity there. So to me, this was very interesting when I first saw this, because it's like Kelvin-Helmholtz instability for inviscid flows, but viscous. Okay, so it's quite an interesting take on that. And there are some similarities with Kelvin-Helmholtz, as we will see. Okay, so everything else is the same. The only change is the boundary conditions. So in the if you don't have slip, then the kinematic conditions on either side are really the same. But here you have to use one of them, and then the other one is continuity of normal velocity. So that's the first tiny change. These are completely compatible with what happened before. This is without loss of generality. You can do this for the other problem too. Then I have the normal stress balance, which is here, tangential stress balance, again, the same as before. But now what I need to replace is the continuity of velocities at the interface with a Navier slip law. So this is just that written in vector form. If the slip length, which is b in this problem, if it's 0, then it says u1 equals u2. Okay, in the tangential direction. And of course, they're also equal in the normal direction. So this is the new condition I need to impose. Now I could replace this with a T1 there because I have continuity of tangential stresses, and that doesn't matter. These parameters are just there for scaling purposes to get the dimensions right. It doesn't matter, they can be absorbed in the B. Okay, so if you do all this, then again, this is the new equation is here. This is the continuity of velocities, if you like, and L is the dimensionless slip length. So if this is 0, all this term is gone, and U1 equals U2, V1 equals V2. So that will be satisfied identically. Therefore, you need to go back and introduce another equation. So, and these are just typical basic profiles. They're still linear in Y, but they have a jump of size L, which is the slip length. Okay, so what do? Well, we can do nonlinear theory as well, but we can also do a linear theory of this. That would be quite useful to do for the full linear or Sommerfeld problem. So I'll begin with that. So this is 3 different configurations just to set the stage. This is no slip. This is a little bit of slip, right? L is order 1, but and this is L equals infinity, right? An infinite amount of slip. So this is even closer to Kelvin-Helmholtz. Okay, but it's amazing that this can be done analytically, in fact. Okay, and so what we want to do is to say, well, if you get a solution for this, how big does L need to be to get that? And sometimes L is 1 is good enough. So it's not a crazy limit to study. So how do I do linear theory? Well, again, linearize the equations. I will get 4 Sommerfeld equations in each region. Here they are, right? Lots of parameters again. Now I have the slip length as well. I have a Froude number. Now I have gravity as well. And what we find is that slip destabilizes the system. So this is kind of a new instability. Even in situations where the thinner layer is the less viscous, you can still destabilize it due to slip. That's what this shows. okay, I don't think I have too much time, so let me see if there's anything I want to say here. But yeah, so I mean, you can do long wave theories, and this is maybe we'll just look at this example. If the imaginary part of C, so this is a long wave theory, so I just look at the first time C becomes imaginary. If it's positive, I'm unstable, and if L is 0, I'm stable for all values of the parameters. But then as I increase L, I become unstable. So this shows that I can induce instability with the slip. You can also do the short wave limit. Okay, before that was a long wave limit. That's a regular perturbation. The short wave limit, you need to introduce boundary layers near the interface and all these things. Again, it's very doable, and you get exact expressions. And this is what happens if you solve the full dispersion relation. So this is the growth rate versus wave number for a case where surface tension is not present. Okay, so I remove surface tension so that I'll be able to see something at large K. So this is the long wave result, the analytical result. This is the one-term short wave result. This is a two-term short wave result. The effort to get this and this is the same. It's just a bit more algebra. So, and then in between we get where we solve the equation exactly, we get a connection of these two branches. So again, what we see is short wave instability for large wave numbers. Okay, and then there's another phenomenon that comes about, and that's the following. Let me try and show it here. Suppose I start with a situation where if there is no slip, the flow is stable. And then I start increasing slip. So I increase it from 0 to about 0.01, which is not a huge value. So what you see is that, so this is the 0 curve, so everything is stable. And then as I increase L, you can see this curvature poking up through the axis, and then eventually you get a band of unstable wave numbers. And this is identical to the Turing patterns that you see in biology. It was first analyzed by Turing, 30-something or 45. So, and then I have surface tension, and that's why everything decays far away. So, so this is kind of a very interesting phenomenon, because if you take so what we do here, we did the same analysis as before, the nonlinear type analysis as before. The only difference is now we put the thin layer on top. So just to complete everything. And again, surface tension is there. This is gravity now, and R is the ratio of densities. So you can be stable or unstable because of gravity, depending on what the ratio is. Then there is a term like this that involves the slip. Okay, beta is the slip. So that's like KdV. And then there's this non-local term, which is now given by this expression, F double prime at 1 now because I'm at the top. But it's a different equation, okay? And the equation, it's more complicated, okay? It doesn't matter. More complicated, you can still write down Airy functions and do all these analytical things. But the growth rate is here, right? So again, you can get instability because of that term. Now, what was interesting for us was the following special case, and then I think I'll almost stop. If I take a case where m is less than 1 and L is 0, so m is less than 1 means that because it's the thin layer on top, right? M is less than 1 means the thin layer is less viscous. So it should be stable. So L is 0, everything is stable. Then we can show analytically, because we have a good handle on this, on all these area functions, we can show analytically that even for small m and small l, you can get instability. And this is a manifestation of that instability for not so small an m and l. Okay, some 0.5 or something. But it's exactly this Turing type instability. Okay, so this would not be there without slip. And then we can compute traveling waves and do their stability, and that's what's shown here. Again, solid and dotted lines. One thing we have not found is bistability for this problem. Not only one of them is stable, but maybe there are some. We just haven't looked far enough. And these are different Reynolds numbers. As I increase the Reynolds number, the waves get more nonlinear. Okay, so I think I'll come to the end and see if there was anything I wanted to point out. Extensions of 3D are important, so we're looking at those. And all these non-local type analysis is pretty typical in all sorts of problems, including path dynamics and anything with species that diffuse in a multi-scale environment. So yeah, with that, sorry for running late, and I'll stop there and take questions.
Thank you. This was fascinating. I have a couple of questions, but my most urgent one is about the polymer liquid-liquid interfaces, because it's relevant to what we do at CIMEA. Have people looked at the molecular dynamics and quantify the size of that interface region?
I think Koplik and Banavar, they they said it was I think just a couple of how do you call it, the core size of the maybe not, these are molecular, so I think, I mean, that was 20 years ago. There's probably it could be quite interesting to see, well, and also see the transition, I guess, from
exactly
full slip to
quantify that size in terms of the properties of the polymers at that mystic level.
Yeah, one other simulation that was done was by Papageorgiou et al. Omar Matar is involved in that from Imperial, and I think what they did, I can send you that paper. What they did is they, I think they were at the other limit where you did get entanglement. So then they tried to model it as a layer where the density varies across the layer, and they suggested that's another way of maybe doing it. But for a mathematician, that's bad, right? Because then it's sharp interfaces, that's much better. Otherwise, you have to do it fully numerically.
How about the continuity of the tangential shear? Because I guess if we are violating the continuity of velocity, could you see a case where you could have like a shear slip kind of? That's
that I think that's an excellent question. That bothered me as well for a while, but I couldn't really think of a way where you could get a jump in that tangential stress, and you can do this. You can do this from first principles in infinite domains, right? So suppose suppose you have it in a channel and then you extend the walls out to infinity, and then you have two simple shears. Then they have to, right? They have to match. That tangential stress balance has to be there, even even if there's no slip. So I think it's okay as a model. And what I'm doing now, there's been some other experiments where they put bubbles, gas bubbles at the interface, so that the interface now has a piece that's no slip, and the piece where there's the gas bubble. And that's a little bit like a shear free on top, shear free on the bottom. So building something like that is also for social. I'm not done.
It depends on also like the conditions. I presume these are in melt.
These are melts, yes. Yeah.
I mean, just as a follow-up, actually, she stole my question, but I'm just wondering, of course, as you say, it's much more difficult, let's say, when you don't have an abstract there, discontinuity. But if you take, let's say, as an input from detailed particle simulations, exactly what's happening at the interface. So is it possible to use it as a given, let's say, and then try to build on
I
top
think
of that?
so. I think so, yeah.
Because that's then a direct, let's say, coupling with the microscopic scale.
I think so. And I think also if the layer is very thin, then you can do an inner solution and see what the conditions should be.
Yeah, I can
So
play with
I
that.
think
Yeah,
it's,
no, but this is very interesting. And if I may, as more from curiosity, here you have the bifurcation, correct? Where you have two solutions, two different, right? But you might have even more afterwards. right?
yes. Yeah.
So
yeah,
you might
have.
see. So did you
There's-
see this full, let's say, chaotic transition to the chaotic behavior?
We only looked at traveling waves. There's an infinite number of bifurcations. Phase 1, 2, 3, and they keep going. And if you and they all coexist.
Okay.
They all coexist because these norms just keep growing as you.
But at
increase
some
the
point, is it
parameter.
probable to see like a fully chaotic behavior, let's say, analogous to?
I don't know how I would see that from the steady state bifurcations, but from initial value problems, yeah, that we're trying to do that now. I'm sure it will.
Thank you. It was an excellent presentation. More questions? Comments?
Yeah, of course.
Maybe there are some before from the people online. Yeah. There are so many different phenomena here.
One other question is about the curvature of the quad device. Is this being taken in? Yeah. Is this being accounted for in general? Like, have people looked at this?
Not that I know of in analytical studies. I mean, I know for sure that for falling films, people have accounted the way I showed it, it was like the plane was infinite, but it has sides, right? So people have accounted for the sides in that case. So the phenomena are pretty much the same. They just get modified towards the end, the end points. I think the speeds in these devices are not high enough to get centrifugal type effects.
Yes,
I think that's really
I'm aware that's not the case. I'm just wondering about the curvature of the channel, whether it could have any effect. I guess it depends on the application.
I think it probably would for Oldroyd B, right? I mean, immediately you've got hoop stresses. Yeah, that's a good point. Yeah.
Okay. Yeah, we can carry on.
Yeah.
Well, yeah. Thank you so much. It was
Okay,
amazing,
thank
amazing
you.
talk. Thank you.